I'm Shane Caldwell. This is Training an Autonomous Pentester using simulation and deep RL. I'm going to try to keep talking into the mic and not turn my head. So if you will forgive an understatement, a huge understatement, I would say that AI can do a lot of stuff. It's been a pretty prolific technology of the past decade or so. It's really good at classifying pictures of cats. It is currently the best Go player in the world. It has been 2 years away on driving for 10 years or so. But you know, between Andrej Karpathy and George Hotz, someone's going to get it before too long. It can do whatever AlphaFold is. I Googled it. I don't understand. Maybe you do. But what can't AI do yet? It cannot yet hack the planet, and I find that unacceptable. So let's fix that today, or at least start moving in that direction. So just as an overview of where we're going, we're going to talk about what pen testing is and why we would bother automating it. We'll talk about reinforcement learning as a potential solution to do that automation. We'll talk about Metasploit and sort of its role as the correct level of abstraction, I think, for automating pen testing. We'll talk about how to deal with how bad RL wants data and how hard it is to give it all the data it wants. We'll talk about the development of Metasploit Gym, which is a reinforcement learning environment I've written that allows you to take your Python agents, your neural nets, and interact with real networks using Metasploit. We'll talk about what remains to be done. So first, a little bit about me. I'm a recovering pen tester. Did the job for about 2 years. Then I became a machine learning engineer and am now. My intersection, or my interest, is that intersection between AI and security. So just like two really esoteric things that people tend to not want to talk about. So let's first start with what pen testing is. In pen testing, you are being paid to hack people, which is cool. It's fun. Your goal is to perform a security test. So your client has some network infrastructure. They want to know how secure it is. So you will try to break it down, and see what you can find. So there are a lot of flavors. So if this isn't the flavor that you do in particular, I hope you don't get mad at me, but in the one that I was familiar with when I was doing the job, it was black box, right? So you'll start with what is available from the internet that represents the attack surface or the perimeter for the client. You'll attempt to exploit those various pieces of the perimeter. You get through into the internal network, which tends to be way less secure because they didn't think you were going to get there, and then you just sort of get into all sorts of trouble. You see how, what kind of damage you end up doing. At the end, you submit a report. This is why they have you do this. It's not just for fun, right? They want a report showing, hey, these are all the holes that you found. This is how you would remediate them. So, someone who is slightly more malicious than you doesn't actually exploit them for profit. So if we can just do a pictorial example. Once upon a time, I was a skull in a laptop, and I was looking at the internet, I can go through the internet to a client's external web server, right? So the world would be very secure if we just stopped networking all our devices, but we found out they're like way more useful that way, so we tend to network them anyway. So assuming that this part goes well and I can get into the perimeter, well then great, now I'm Red Skull on the box. And that's useful. We'll call it remote code execution. You might think of it as like a shell on the machine. What that allows you to do now that you're on the box is look around, right? You can see network interfaces you couldn't otherwise. You're now inside the network. You can see different machines that are more local. You can sort of move laterally around the network and continue to, hack stuff. So the way this sort of works in practice is you have a full network. So you have like 20 plus externally available IPs, and then whatever is, on the actual client network once you get inside. There could be machines for days. You have limited time to perform the test, so it tends to be like 1 to 2 weeks. And you have to balance, or at least I found I had to balance these two distinct elements. The first was breadth. So you're given these IPs that are in scope. You have to scan them. You have this like CIDR range or maybe individual boxes. And you're looking for obvious vulnerabilities. When I say obvious vulnerabilities, I mean something that someone has already exploited. If I Google name of service version of software and exploit DB, something comes up that is like code that runs that will exploit this service. And my job is to look at literally as many of these services as possible and see say confidently at the end, like you're good or you're bad. If you miss something basic here because you didn't do enough recon, that's going to be a huge problem. Your client's not going to be happy with that, especially if someone comes in and actually exploits that later. So you've basically failed them if you don't do that breadth very well. But the thing people like in this field, or at least the thing that I found that I enjoyed and a lot of people I worked with also enjoyed, is something I would call like more depth pen testing. And it's a little harder to define. It's like you're doing your scans, they take forever. At one point something pops up like it's a web server, but it's on a non-standard port, and you start interacting with this web application, and as far as you can tell, it's not like a standard one, it's like someone made it custom, and then you're starting to like fuzz some parameters, you're getting stack traces that seem kind of interesting, like maybe exploitably interesting, like this is cool, this is the good stuff. That's where the dopamine came from, for me at least. That was the good brain juice. The problem is I would love to spend all day on the depth thing, but to do right by the client, like we said, you've got to make sure that breadth is covered, right, that you did right by the client. So the adult thing to do is you take the fun thing that you like a lot and you time box it. So if you have a test that lasts a week, maybe it'll take like 4 hours of one of your days to like try to do the fun thing. And if it doesn't work, you got to step away, and get back to doing that breadth stuff. So most of the time, to do right by the client, you're doing breadth type work, but the reason you like this job is because of the depth stuff. The solution, actually, it turns out, is to wait a couple of years until you have junior pen testers to do the breadth thing for you. That did not strike me as possible at the time because I'm very impatient, so I decided to quit my job, go back to grad school, and study ML so we could try to automate that breadth stuff, so I could just do the depth thing all day long. And during that time in grad school is when I was more formally introduced to reinforcement learning. So reinforcement learning is a field of machine learning, a little different from supervised or unsupervised learning, and it involves focusing on agents, agents that can interact with their environment through different actions. And what they're doing when they interact with this environment is they're trying to maximize a reward signal. It's got a great resume. Basically, most of the really cool things, in my opinion at least, that AI has done over the past decade have all been reinforcement learning. So if you like AlphaGo, if you like the best Go player on the planet, then you're into reinforcement learning. The OpenAI DOTA bot, Atari, these are like problems that we used to consider pretty human kind of problems, and RL's good at knocking them out. But what do you need? What needs to be true before you can apply reinforcement learning to your problem? First, you need to be able to break the problem up into an action space. So for a given turn, at a given time step, what moves can the agent make? Then you need a state space. So at what level of abstraction will you represent your environment? What is the agent going to get to see before it makes a decision about what to do next? And then both of these have to be vectors or matrices because that is the language of deep learning models. That's just what it is. And you have to have a reward signal. So let's look at a super simple example, connect for. So the action space, pretty obvious, right? You got 8 places to drop a checker. There's only so much you can do in connect for. Great, we can represent that as a vector pretty easily. 0, 1, 0, 0, 0, et cetera. That could indicate dropping a checker in the second column. It's one by a vector, we're good. That's an action. The environment, on the other hand, we could represent it as an 8 by 8 board. So what we know about this board is that it is 8 by 8, and there is either a red checker, a yellow checker, or an open space. So we can kind of arbitrarily choose, okay, red is -1, yellow is 1, and open space is 0. There you go. The reward signal is also pretty straightforward. You have a one-on-one game. You like to win. You hate to lose. You can sort of dole out your reward that way. So the agent will start very bad. It'll pick moves essentially at random. But as it starts to play more of these games, it'll start to correlate certain versions of its environment and certain actions it's chosen that result in a win or a loss. It'll start to learn oh, when I do this, I win in this situation. That's great. So with all that stuff sort of set up, you can now have you can kind of take your pick of any deep reinforcement learning algorithm that has been made in the last couple of years. Through self-play, take these 2 agents, they play against each other. You will, in 3 hours on your laptop, have a greater than human player at Connect 4, which is cool, not as cool as hacking. So let's but let's talk about the benefits of RL, right? So it's a very general problem formulation, right? You can't make everything look like a classification problem that neural nets are good at, but like agents interacting in an environment and like doing stuff, that's like more general. There are a lot of things that could fit that sort of description, right? And as we've discussed, its resume is great. It's crushed some problems that we thought required human intelligence. We used to say like, man, if you could play chess, that'd be AI, right? And now chess is lunch, man, we can do more. So that seems like a good place to start. But it has its drawbacks. RL has its detractors, and they're not wrong either. It's extremely data hungry. So when I show you the resume of RL, you're looking at a lot of things that are games, right? They can be run at faster than real time. You can collect a lot of data very quickly. It also requires a cleanly delineated action and state space, which ends up being a more difficult and philosophical question than you might initially believe. And it's difficult to train due to reward hacking. And this is, we're gonna look, the video still works. We love that. So before OpenAI got into large language models, they used to be into training reinforcement learning agents. I thought that was cooler, that's just me. But this is like the canonical example of reward hacking. What reward hacking is when you give an agent a reward for something and it finds out how to do the thing that gets it reward, but not the thing you wanted it to do. In this case, the agent is a boat. It's supposed to win the boat racing game. But like we said at the beginning, those random actions you pick are probably not going to lead to success, right? So if you only give reward when the agent wins the race, well, you're never going to get anywhere. You're never going to win the race. So they gave out reward for picking up this little speed boost, this power up. Because, if you go fast, you probably win the race, right? Well, this agent is a genius, and it figured out how to just get in a perfect loop that allowed it to pick up like 3 speed boosts and just continue to do that. And so it was wire heading at this point. It had no other desire for reward. You can see all the other sort of boats just like lapping it. It's kind of tough to get one of these to train in a way that it is aligned with sort of the goal that you have. So that brings us to pen testing, right? So I really wanted to automate pen testing, and I really thought reinforcement learning was the solution, but determining the action and state space was challenging. For those of you who have done the job, you know that there are a lot of tools involved in network pen testing. There's a lot to think about. So picking a level of abstraction to sort of work on that is like not so abstract that it's meaningless and not so like down in the nitty gritty that you are orchestrating like tens of thousands of tools and like keeping their state and like figuring out what that even means. Like the software engineering challenge alone of cajoling all those tools like sort of kept me from working on this for about 2 years because I just didn't know how to move forward with it. Then COVID happened and I had a lot more free time. And like 3 months into that, I was reading network security papers at 2 a.m. as you do. And I came across this guy, Jonathan Schwartz. He was writing on his work. He was doing simulations for security. And in his talk, or his thesis that I'm browsing through, he's sort of arguing for why simulation is okay. And in his argument, he's like, you might think this is too abstract, but we're in the security realm, we're already moving towards abstraction. So take Metasploit, for example. People who use Metasploit, they use it professionally all the time. You don't need to know how the exploit works, right? You're working on this certain level of abstraction where you just sort of know, this is the service I'm attacking, this is the port, this is the IP. Those lower level details are handled, and that's still doing real pen testing. And I was like, that's a really good idea. We should do that. So in that, I felt like I'd found the perfect layer of abstraction to sort of apply reinforcement learning to that problem, and that was at the Metasploit level. So let's talk about what Metasploit is real quick. So Metasploit is this open source framework for pen testing. It is a bunch of Ruby code comprised of modules to sort of do everything you might do during a penetration test. It's a super common tool. So it handles scanning, so you're looking at your targets, these machines, what's their operating system, what are the ports, et cetera. You can exploit common vulnerabilities. There are over 592 different services that can be exploited. There are more written all the time, and it's just like thousands of people writing these PRs for oh, there's a new proof of concept. Let me put that in Metasploit. That's just a common thing, which is great. Privilege escalations, that's if you have a lower privilege shell, you've exploited a box, but you're running in a normal user context. You really want to be running in a root context. So they have tools for that. And then grabbing loot, so to pull sensitive files off of hosts, generally as a way to prove that you were on the box, that you said you were on to a client. It also might contain information that gives you sort of further access to the network. And it's really easy. You select a module, you configure some parameters that are related to the host, most generally what IP, what port, what do you want me to do when I get there? And you execute and you're off to the races. Metasploit also keeps a lot of state. This makes sense because when you are pen testing, if you don't have an audit trail that is like, with a bullet, you're in trouble. Because when you're on someone else's network, even if they're paying you to be there, if something breaks while you're there, it's your fault, as it turns out, no matter what you were doing. As a consequence, Metasploit has a really slick database with all the hosts you've encountered during your test, all the services running on all those hosts, all the exploits you've run or tried to run, all the files you got off the machines, and any credentials for those machines. That sounds a lot like a state and action space to me. That's a level of abstraction I can work with that involves actually, exploiting boxes. So I was satisfied with that. So to that end, I built the Metasploit gym, which is a reinforcement learning environment that allows deep RL algorithms to interact with networks of real machines using Metasploit as a sort of conduit. This is possible because Metasploit, though written in Ruby, has a gRPC service, which gives you access to its API. You can do basically everything you could do from the terminal command line automated. And this guy, Dan, whose last name I'm going to mispronounce, I'm sorry, Dan McInerney, okay. He developed PyMetasploit 3, which gives this excellent API for handling all the communication with this RPC service. It probably knocked like 6 months off my development time. He's a hero. We love him. Let's talk about the state space that I made, so you guys can argue with me over whether it's complete or not. First, so our environment that we're representing here, the sort of atomic data structure here is going to be the host, right? So we're going to represent the host as a flat vector, and there will be many hosts. First, we have to pick, we want to store the information of the address in the subnet and make that available to our agent. Sort of a limitation to call out here is that every time you pass your environment to your agent, so your agent looks at a vector, or a matrix rather, representing your environment, it has to be the same size. So when I start training when I start training an agent, I have to make the decision like how many subnets and how many hosts per subnet are we going to build for here? Because each, you're going to get a matrix of rows. Each of these is going to be a host, and I have to decide how many hosts ahead of time because I can't make that matrix bigger later. So for example, if I say 2 subnets, 8 hosts on a subnet, well, that's 16 possible hosts. It'll start all zeroed out, and as I see more hosts in the network, or as my agent sees more hosts in the network, I'll add them, but there's sort of a hard limit on size, which is, it is what it is. It's a limitation. Loot, that's an easy one. So we'll have one index of this host vector that's just for loot. It's an integer. Every time you get 1, you sort of increment that number. That's easy. Operating system, we'll have a single number, another binary flag. Is this Unix? Is this Windows? That'll be really relevant to what kind of exploits we pick, as it turns out. I didn't include Mac because there aren't that many Mac-specific vulnerabilities. Like, you can roast me for that, but in terms of what I was working with, it's true. Credentials, another single number, sort of binary flag. So 1 if you got creds, 0 if you don't, that's great. We can store a reference to the credentials within the Metasploit gym environment. So if the agent chooses to use an exploit that requires these credentials, then we can just provide that at runtime. Otherwise, the agent just knows, I have some. Services, this is sort of where you start making a lot of big decisions. Obviously, if I made the vector big enough to include like every sort of port, and then whether it was running TCP or UDP, that would be a very, very large vector. That's not a proof of concept, that's too hard. So I picked some ports, and I did that through the rigorous method of letting Nmap decide. Nmap publishes, it's like the biggest scanning tool on the planet, and they publish a list of like, hey, these are the ports that people scan, top 20. So I was like, great, give me the top 20 TCP services, that's what I'm interested in. So we have 20 elements in this vector that are just for like, hey, these are the services that are on these ports, binary flags all around. And we have a separate data structure to handle port mapping. So say FTP is on a non-standard port, that's fine. The agent just knows FTP is there, and we'll handle that port configuration when it comes time to execute and exploit. Now, if it's the same service, again, this is a size issue, right? We need our host to be a consistent size. So if the same service is on multiple ports, we're just going to ignore it, which is like not great for services like HTTP. There might be like a bunch, but we'll just pick the first one we find and we'll throw the rest out. Vulnerabilities, those are important. So if we've exploited a vulnerability on a machine or we've tried, we want to make sure we store that as well. So for each action we have, we're going to add that to our vector as well. So we'll have 20 different, or I do currently have 20 different exploits that Metasploit Gym supports, which are like broken up between exploits, privilege escalation, loot gathering, scanning, all that stuff. And then privileges, that's super important to know. So when we talk about privileges in the security context, we're generally talking about what context are we running in? Do we have system access? Can we do whatever we want? Or are we in some limited context? So we'll keep access, that information as well will be exposed to our agent. And then that's for one vector, right? That's one host. So how do we make a network matrix? Well, you start with the host vector, and then you put another host vector, and then you stack those up, so you got a network matrix. And then we'll throw one additional row on the bottom, and that will give the results of the last action, whether you were successful or not. That's just going to give the agent a little more information as to like, hey, you did the right thing, you did the wrong thing. The action space, straightforward. I already said we have 20 different exploits. The action space is basically pick a host, pick an action, pick a service, you're ready to go. That is also represented as a flat vector. Reward was something I just sort of tried to reverse engineer from how good things felt when I was pen testing, which is sort of arbitrary, I guess, but gathering novel information is good in pen testing. So if you learn about a new machine, I'll give you 5 for that. If you check an exploit against a machine and it'll run, as far as Metasploit is concerned, you get 1. Gathering loot is going to give you 1 reward per unique file and 5 reward for password hashes. When I say this is for novel information, what I'm saying is we're trying to avoid that like boat spinning in circle, picking up speed power-ups thing, right? If we gave it out each time you scanned, then any agent under the sun would just learn like, I'm just going to keep scanning that thing. This is free. Like this tastes great. So only for novel information. And the same will be true of exploits. So if you exploit a unique vulnerability on a host you haven't exploited it on yet, that's going to be 10 reward. And then if you get super user privileges, that's all the marbles. You got root, we love that. We're going to be 20 reward for that. So there you go. So we have this environment. What are we going to train it on? We'll start with Metasploitable. So if you're in the security space at all, Metasploitable machines are like super exploitable. They're very bad in terms of security. They're essentially test machines, wherein if you pick like random actions from Metasploit, there's a good chance you're going to pop a shell in that box. They're easy to exploit, but that's good actually because think back again to the boat example. They had to find a way to give it reward that wasn't associated with winning because just picking random actions is not going to get you anywhere in the start. But if a machine is super exploitable, then picking random actions is more likely to lead to like actual reward in the way we want it. So that's great actually. In terms of training speed, this is where things get a little dicey. So you're running real commands and real exploits against real machines. That's slow, actually. I don't know if you've ever run an nmap scan on every port that a machine has. It takes forever, man. And to simplify turns, each command needs to be entirely finished before I read in state. This is like a super common problem I had early on as I would kick off a scan and then I just like keep doing actions or whatever. And then my scan would complete after I'd taken like a random like SSH brute force action or something. So my agent's like, oh, I ran SSH brute force and now I learned all this stuff about the box. That was great. That's not great. We'd like to make it asynchronous, but to ease it up, we're going to say, you must completely finish the command. And you're running virtual machines that you have to reset to a known good state after every episode. That also takes some time. This is just running on my local machine. I found that I was able to collect 256 time steps every 7 minutes, which sounds okay until you look at the DOTA bot that OpenAI made. It was getting 256 time steps every minute for each of its 57,000 workers. I don't know if you guys are good at math. I'm not, but they were getting way more data than me. So we have to go faster. How are we going to get more data fast? Simulation, I think, is a good idea here. So we can take all the same abstractions that we already made to get our sort of Metasploit gym running, and we can build it out as a mathematical model instead of a simulation or instead of a real network to allow us to train faster. So we're going to keep the action space and observation space 1-to-1. This is crucial. So as far as our agent is concerned, it doesn't know whether it's interacting with a simulation or a real environment. So how do we do that? Math people figured that out for us actually a while ago. It's called a partially observable Markov decision process. What do you need for those? Well, you need states. Great, we got states. We picked states already. We're good there. We need actions. We already have actions. We need T, a set of conditional transition probabilities. Oh, we don't have that yet, actually, but that's the one we need to do. And the reward function is going to be the same. So when we talk about conditional transition probabilities, what we're saying is for a given action in a given state, there needs to be a probability of success or failure, and then given success and given failure, you need to know what the state looks like in each case. So for example, I can simulate a machine that is running SSH, and then I can run the SSH command against it, and then I will decide what is the probability that that was successful, and what reward does it get if it was successful. This enriches Jonathan Schwartz's work, actually, the same person whose paper I read that sort of inspired all this Metasploit stuff. I've simply expanded it to be compatible with Metasploit's data model, so it interacts with real machines. So you can generate a machine over YAML. It's kind of easy. We'll look at the salient points. So for example, we can say this host is running SSH. It has an exploit that it's vulnerable to, which is this SSH exploit. It's a Linux-specific one, and if you run it, if you run the SSH vulnerability, there is an 80% chance that it's going to be successful. And implied in this, but not stated, is if you run like an FTP exploit against an SSH, that's 0%, right? We're not going to let that happen. What that means is because that is opaque to the agent, we can use the probability to sort of start to bias the action, the agent towards certain actions. So we can learn super basic stuff that it would take us a long time to learn if we were learning against real machines. For example, SSH vulnerabilities tend to work against SSH, not just sort of randomly. So we can teach it both the actions that certain services should be associated with and the general loop of, hey, you should scan, then you should exploit, then you should get privilege escalation, and then you should scan new subnets. And we can do that all in simulation. So you want to see a demo, right? I trained a deep Q learning agent against Metasploitable 2 using the Metasploit gym environment I created. I ran it against a random agent. So for those of you not familiar with reinforcement learning research, the way you show if you did something is pick actions at random, and then you see if you beat that. If you beat random, you're doing great, academically speaking. So that's what we did. So each agent had the same sort of action space. It was working in the same environment. And we ran that for 100 episodes, which means at the end of an episode, you're going to reset the environment to the beginning and run it again. Let's look at bar charts. So the average reward over 100 episodes, the random agent, just sort of picking stuff, did get lucky sometimes. It ended up with on average 11 points of reward. Again, Metasploitable is very exploitable. You can just pick random stuff and it'll work out for you. The deep Q network, on the other hand, got 35 reward on average, which is the maximum available from the environment. Then the number of episodes root was achieved, so the number of sort of episodes wherein it was ended not because we ran out of time steps, but because, hey, you got root on the only box I care about. We can move on. For the random agent, that was about 1/5 of the time, and for the deep Q network, it was always. And then the average steps to root. So how many time steps did it take to sort of get to root on this Metasploitable box? The random agent has no strategy. It's just picking random stuff. So it took on average about 10 if it got there. And the deep Q network learned this kind of two-step, this sort of minimal step that I wanted it to learn, which was cool. And let's look at a play-by-play just to make that sort of concrete. I'm not going to do a live demo because I'm crazy, but not that crazy. And I don't trust hotel internet, man. I'm a security guy. So we're going to start by looking, I'm just going to show you screenshots of the terminal of sort of what it looks like over the course of one of these episodes. So this is time step 0. We're looking at a target IP. You see the IP there, host name Metasploitable 2. So this is the view from within Metasploit at the beginning. So you're at time step 0, no hosts, no anything. So faced with this and an in-scope IP that I provide, the agent will first choose to do a port scan, good choice. And at the end of that port scan, it has a list of sort of all the services that are running. There are a lot because it's intentionally vulnerable. And then for the two-step, or for time step 2, it will choose to execute this particular FTP vulnerability, and it will be successful. So from Metasploit, you'll just sort of see this command shell pop up. And then when you look at that command shell, you'll connect to it, and you'll be like, who am I? It'll be like root, and you'll be like, sweet, like this is great. So it did it in this sort of baby case, right? Metasploitable is a very intentionally vulnerable machine. I did not solve pen testing just because I can automatically sort of teach an agent to do this. So future work could involve adding sort of all of the exploits that Metasploit has, so a full action space, and then programmatically creating more realistic network scenarios. So a one machine does not a network make. Network topologies are a little more complicated than that, and they have like a variety of different sort of shapes that we'd want to know about. And do that early training on the simulator, as I discussed, and then move to real machines that are created, like scripted with a Vagrant or whatever, to actually fine-tune our weights then. Pen testing is also an interesting environment to explore the practical alignment problem. So the alignment problem is when, you've heard it, really smart people are like, super intelligence is going to turn us all into paper clips because it's going to maximize its reward by turning people into paper clips. And you're like, I don't know about that. The classifier thinks my cat's a toaster, so that's not really at the top of my list of concerns right now. But alignment research is real, and it's a really interesting area of technical AI safety, where you're looking at general problems of like the boat that picked up the power up instead of winning the race, of aligning the sort of the reward we're giving agents with our actual goals, right? And pen testing, to like make this work in production environments, you'd have to solve some of those problems. So for example, discretion is the better part of valor for pen testers. There's many times when I was working a job and I would see a service that looked like super exploitable, then I'm Googling this service, and it's like, yeah, you can run this exploit, but it might crash the box. I'm not gonna do that. My professional liability insurance is expensive. So I'm gonna send an email, I'm gonna put it in the report anyway. An agent seeking reward is just gonna exploit it, come what may. It wants that sweet, sweet reward. That's a problem. There's also another problem would be like, if I'm a pen tester, I'm on a network and I see a bunch of client machines, right? Machines people are using for email, Excel, whatever. And I see a vulnerability being expressed. As the pen tester, assuming that's in scope, I'm gonna pop 2 of those boxes max. The first to see that I was right, and the second to verify that like they probably all share this configuration, and then I'm gonna write a report that says, hey, all 350 of your machines, this probably applies to them. But my bot here would just be like, 300 free reward juice? Yeah, man, and it would pop every single one of them. And then when I talked to my client, was like, hey, your IT guys have to clean every single box on your server, actually, like every single box in your network, because I wanted a lot of reward. Then again, I'm gonna get fired at best. At worst, the professional liability insurance is gonna come in clutch. So this is like very much L2 autonomous pen testing, let's say. But some takeaways now. A lot of interesting AI research goes undone without the infrastructure to work on it, right? So like making the gym was mostly about sort of getting a data model from Metasploit that I thought would work for an agent, and then sort of cajoling it through this RPC service to, when an action is selected, make sure that gets run. That's all software engineering, right? The AI parts of this project, like actually training the model, took me like a week. They're writing the software so I could train that model against it. Took me like 6 months and like years of thinking about it. So if you have a domain that you care about in programming skills, this seems like a good audience for that. You can create infrastructure that makes it easier to bring AI research to your field. So if you have a gym for your problem, like you're into, I don't know, Team Fortress 2, and you make a Team Fortress 2 gym, like now people will write, stuff to interact with that. You've now lowered the barrier for entry. And also, you might want to use Metasploit Gym. This is a functional programming crowd, so you won't understand this, but I was like passing state around a lot while I was writing this, so it got uglier over time. I'm not ready to open source it yet, but I will by the end of the year when it's a little less runs on my machine. When it's ready, it'll go here under Freak AI Metasploit Gym. And I'm going to post this slide deck on Slack after this, so don't worry if you can't see it. So if the work sounds interesting to you, to like really do it, all the stuff I'm talking about, like I need to handle this full action space, and I need to script a lot of machines in different network topologies and train a distribution that, like, to create a distribution that is representative of real life and then train an agent against that, that's a lot of stuff. So if you're an engineer, a deep learning researcher, you're into CI/CD, DevOps, you're a pen tester, let's work together. This is all like open source stuff I'm doing in my free time, and I would love to work on it with other people. So send me an email or join this Discord link, and I will be there, and we can talk shop. So thank you. If you have questions or want to contribute to Metasploit Gym, There's my email. I spend like way too much time on Twitter, and you can find me there. And then again, there is the AI Discord where I'm hoping we can do this work going forward. Thank you.